Hello students, welcome in your quantum mechanics lecture. As in our previous lecture we have talked about particle in a box, very simplest example, and in this lecture we will talk about step potential. We will consider a potential barrier. So by definition you can say a potential barrier, if the force acting on the particle is zero or nearly zero everywhere except a particular or limited region, it is said to be a potential barrier. So we consider that along the x-axis we have a region where the potential V is equal to 0. At x equal to 0 there is some discontinuity, and if x is greater than 0 then there is some potential, say V equal to V naught. So this is like a step potential. So this is a barrier. This is a barrier. Classically you can say, like in this region there is no hurdle, but as we reach at x equal to 0 there is some step height, that is there is some hurdle, so which restricts our movement in this region, that is x is greater than 0 region. In x is greater than 0 region, and this is x is less than 0 region. So that means we have no force acting on the particle in region x is less than 0, and in the definition of physics we can say that there is no force in the region x is less than 0, but at x equal to 0 we have some force, and that force is defined in term of potential V equal to V naught as we reach at x equal to 0 or x is greater than 0. So x equal to 0 is the region where there is a boundary. That means we have a force field acting on the particle is 0 or nearly 0 everywhere except a limited region. That limited region is x is greater than 0 in this diagram. So we have considered a single potential. So at x equal to 0 the force acting on the particle is represented by V naught, and V naught is called the height of the potential barrier, and we can define this potential as Vx because it is a function of x is equal to 0 for x is less than 0 and V naught for x is greater than 0. So we can define this potential step or potential barrier like this. So this region is called region 1, and this is region 2, and in the diagram I denote this like region 1 and region 2. So we have two regions in our diagram. Now in the region x is less than 0, particle moves like a free particle, and as it approaches the step potential in region x is greater than 0, it faces a potential Vx equal to V naught. We can define this like in this manner also. So classically, now before discussing the classical, we have another point here, energy less than the step height. Now we consider that there is a particle and the energy of the particle E is less than the step height. So we have represented the particle quantum mechanically, and this is the energy, and this energy is less than the height of this potential barrier. So we have now potential step with energy less than step height. So E is less than V naught. So this is the case. So this is incident wave, E is less than V naught, and particle strikes at x equal to 0 and bounces back at, or you can say it is reflected, better words are, you can say it is reflected now. So this is incident and this is reflected. So first we discuss the classical view. Now Classically, a particle in region 1 can move freely as the force field is 0 because V equal to 0. And since energy of the particle is less than the height of potential barrier, that is E is less than V naught, and the particle is in region 1 and it will remain in region 1 forever. If sometimes the particle is moving toward the positive direction of x-axis, it will be completely reflected. Suppose you have a ball and you strike it on a wall, then it will bounce back after reflecting the wall. So this is like a ball. So if you throw a cricket ball or tennis ball on this wall, it will be reflected if the height of that wall is less than the height of this wall. But if the height of cricket or tennis ball thrown is greater than the height of this wall, then it will be transmitted. You can say it reaches in the region 2 classically. Here, as we consider the height of that ball is less than the height of wall, so it will be reflected back as the children play, you can see. So this is the classical view. So it will be reflected at x equal to 0. Now in quantum mechanical view, quantum mechanical viewpoint is as the potential V naught is not a function of time, that is it is independent of time, so it is better to treat the problem with time independent Schrodinger wave equation, and we know the Schrodinger wave equation is d square psi upon dx square plus 2m upon h cut square E minus V into psi equal to 0. Let it be equation number 2, let it be equation number 1. So first we discuss in region 1. In region 1 we have Vx is equal to 0 in region 1, that is this is region x equal to 0, the x is less than 0 region is region 1, x is greater than 0 is region 2, at x equal to 0 this is the boundary. So V is equal to 0. In the region 1 we suppose the wave function is denoted by psi 1. So we will represent d square psi upon dx square. We will substitute the value of V is 0 in equation 2. It is 2m upon h cut square E into psi equal to 0. Let it be equation number 3. So we can rewrite it as d square psi upon dx square plus k1 square into psi equal to 0, where k1 is square root 2me upon h cut square. Now it is a simple mathematical differential equation, d square by upon dx square plus a into y equal to 0, instead of y it is psi, instead of a it is k1. So this is a simple mathematical second order differential equation, and solution of this equation can be easily obtained. Now let it be equation number 4. In region 2, we have region 2, that means x is greater than 0, Vx is equal to V naught. So now we will substitute this value V naught as d square psi upon dx square plus 2m upon h cut square E minus V naught into psi equal to 0. Now we know V naught is greater than E. So I will rewrite it as d square psi upon dx square plus 2m upon h cut square V naught minus E into psi equal to 0. So I will write it as d square psi upon dx square plus iota square, because iota square is minus 1, iota square k2 into psi equal to 0, k2 square. So this k2 is k2 is equal to square root 2m v naught minus e upon h cut square. So this is equation number, let it be 5, let it be 6. Now we have two equations. Now we will find out the solution of these equations. So the general solution of equation 4 is d square psi upon a plus k1 square psi equal to 0. So this is for the reason 1, and solution is psi equal to a exponential iota k1x plus b exponential iota k1x with negative sign. So as this is the wave function in region 1, so I will write psi 1 equal to a exponent. A and b are the constants. We will determine the constants, arbitrary constants. And now the solution of equation 6 is psi equal to c exponential iota k2x plus d exponential minus iota k2x. Now as in expression 4 we have k1, here we have iota square k2. So instead of this k2 only, we have iota k2, and here again iota k2. So when iota is multiplied by iota, so it is minus. So it is minus minus plus. So we have minus k2x plus d exponential k2x. So we have, so this is the solution in region 2. So I will represent psi 2. Now we have the wave function of the particle in region 1 and in region 2, and we denote these wave functions with the help of psi 1 and psi 2. Now we have a, b, c and d, 4 arbitrary constants. So we will determine these 4 constants. Now in equation number 7 and 8, in equation 8, where this term is reflected wave, and this term, in this term, this is as the particle moves along the positive direction of x-axis, this term increases. That means as x approaches to infinite, this term is infinite and psi 2 is infinite. So that means it violates the condition that the wave function should be finite everywhere. So we will omit this term, and finally we have psi 2 is equal to c exponential minus k2x, and if we substitute x equal to infinite in this expression, then psi 2 is 0. That means now we have the valid or well behaved wave function for region 1 and for region 2. Now we will determine these a and b and c, 3 unknown constants, with the help of boundary condition. So boundary is at x equal to 0. So the wave function, the boundary condition means the wave function should be continuous at the boundaries. That means the wave function in region 1 is equal to the wave function in region 2 at x equal to 0. So the wave function should be continuous. That means boundary condition 1, psi 1 at x is equal to 0 is equal to psi 2 at x equal to 0. This is the condition for the well behaved wave function. This is the boundary condition. So psi 1 at x equal to 0, if I substitute, then psi 1 is a exponential iota k1 into 0, this is into 0, plus b exponential minus iota k1 into 0 is equal to c exponential minus k2 into 0. That means a plus b is equal to c. This is equation number 10, this is 11. So from the first boundary condition we have a plus b is equal to c. Now the second boundary condition is the first order derivative should also be continuous. That means d psi 1 upon dx at x is equal to 0 is equal to d psi 2 upon dx at x equal to 0. This is the second boundary condition, and the derivative is iota k1 a exponential iota k1. I am substituting the value of x equal to 0, and b minus iota k1 exponential minus iota k1 into 0 is equal to minus k2 c exponential minus k2 into 0. So finally we have iota k1a minus iota k1b is equal to minus k2c. So we can rearrange it as a minus b is equal to minus k2 upon iota k1 into c, or you can say iota k2 upon k1 into c, because I write negative sign as iota square and iota is cancelled with this iota, so it is iota k2 upon k1 into c is equal to a minus b. So this is, let me, equation number 13. Now we have equation 11 as a plus b is equal to c. This is equation number 11. I am rewriting again, and equation number 13 is a minus b is equal to iota k2 upon k1 into c. This is equation number 12. Now if we add these two equations, we have 2a is equal to iota k1 k2 upon k1 plus 1 into c. So we have a is equal to c upon 2 1 plus iota k2 upon k1. So let it be equation number, this was 13, so let it be equation number 14. And if we subtract these two equations, so we have 2b is equal to 1 minus iota k2 upon k1. c is common, so b is equal to c upon 2 1 minus iota k2 upon k1. So this is equation number 15. So finally we have determined a and b in term of c. So with the help of equation 14 and 15, we can rewrite equation 7 and 9. So equation 7 is now psi 1 is equal to, value of a is c by 2 1 plus iota k2 upon k1 exponential iota k1x plus, now I am substituting value of b. b is c by 2 1 minus iota k2 upon k1 exponential minus iota k1x. So I have rewritten equation 7 by substituting the value of a and b. So the final expression is in term of c. This is equation number 16. And now psi 2 is equal to, I will substitute it as similarly like c exponential minus k2x. So there is no need to substitute any value because it is already in term of c. So we have psi 1 and psi 2. So the first term in equation 16, that means this term, in which the term included exponential iota k2x, represents the incident wave, and the second term represents the reflected wave because it is along the negative x-axis. So it is reflected due to negative sign, and it is, we can say, incident due to positive sign. I can rewrite psi 1 equal to psi incident plus psi reflected. So finally we have psi incident is equal to c by 2 1 plus iota k2 upon k1 exponential iota k1x, and psi reflected is equal to c by 2 1 minus iota k2 by k1 into exponential minus iota k1x. So we have the incident and reflected component of the wave function. Now we will look at quantum mechanically, is the particle reflected or is it transmitted, because here we have the dual character. So the reflection coefficient, we will find out the reflection coefficient R. By definition, the reflection coefficient R is the reflected probability density current reflected probability density current divided by incident probability density current. Now you know in our previous lecture what is the probability density current? Velocity into psi star. Now we are looking at the reflected probability density current. So in the region 1, let the velocity of particle is v1, and since we are talking about psi 1 here, it is in region 1, so the velocity of particle v1, and we are talking about reflected, so psi reflected into psi star reflected divided by incident is in the region 1, psi incident into psi star incident. So we will substitute when these two value v1 is cancelled with v1 and psi reflected is c by 2 1 minus iota k2 upon k1 exponential minus iota k1x, and psi star is c by 2 1 star means complex conjugate of psi reflected. That means complex conjugate means I will replace iota by minus iota. So 1 plus iota k2 by k1 exponential iota k1x divided by psi incident is c by 2 1 plus iota k2 by k1 exponential iota k1x psi star incident. So I will take the complex conjugate, so I will replace iota by minus iota k2 by k1 exponential minus iota k1x. So all these terms are cancelled, and finally we have reflection coefficient r is equal to 1. That means we find out that incident wave is totally reflected, and this is same as predicted in classical viewpoint or the classical consideration. Thus in the region 2, that means x is greater than 0, the transmission coefficient vanishes, because reflection plus transmission coefficient r plus t equal to 1. Since r equal to 1, therefore t equal to 0. That means transmission in the region 2 is 0. That means transmission of the particle in region 2 vanishes. But the wave function psi 2, you can see in the expression 17 or in the expression 9, it is not 0. It is c exponential minus k2 x. It means that there is a finite probability of finding the particle in classically forbidden region. Classically forbidden region means region 2 x is greater than 0. The shape of the wave function in region 2. So suppose the particle is moving like this in region 1 and at the boundary. So this is like the wave function in region 2. So it is continuous at the boundary and vanishes. So exponential minus k to x. So as the x increases, this term goes to 0. So I represent it like this. So that is, this is the incident wave and this is the transmitted. This is the transmitted. So the wave function is not 0. The transmission coefficient is 0.